Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Hey, step on inside and we are finishing off Chapter 2 in the Integrated Math 2 Big Ideas Math textbook. Chapter 3 comes next, whenever that next video comes up, but we are still in the playlist for Integrated Math 2. Check the description section down below if you want to find something else leading up to this set where we are looking at the Chapter 2 test in the textbook, as well as the cumulative assessment. I believe the Chapter 2 test is problems 1 through 19, and then the cumulative assessment is numbers 1 through 9. Now, if the cumulative assessment hits things back on Chapter 1, I might spend a quick second just re-reminding you of what that stuff is, but the Chapter 2 stuff, the Chapter 2 base material, at this point we have learned. Or even if we hadn't, and we're putting it to the test. So at this point here, anything I had taught was in a previous section, or even the Chapter 2 review, which you can go and check out. I think that's the previous video that was made in this video series in the entries. So I'm going to go ahead and get started. I don't believe I need a calculator or anything of the sort, but I haven't looked at the problems. But just knowing what we've been working on, I think that they should be pretty standard. I'll let you know what section everything is out of when they come up, because they may go out of order. And so, yeah, just be ready for that. All right, so let's take a look. We have question numbers 1, 2, and 3, where we find the sum or difference, then identify the degree of the sum or difference and classify it by the number of terms. Now, this would have come out of section 2.1, where we do adding and subtracting polynomials and naming them and all this stuff, literally the thing that they're asking you to do. So these are from section 2.1. So we have negative 2p plus 4 times, minus the quantity p squared minus 6p plus 8. Well, find the sum or difference, then identify the degree, sum or difference, and classify by number of terms. So this negative 2p plus 4 can be written without parentheses, and written without parentheses here, if we distribute the negative, that'll be a negative p squared, minus negative 6p, which is plus 6p, then minus 8. Combining like terms, getting it in standard form, not something they asked you to do, but something we really should do, especially when we come up with the degree. So negative p squared doesn't combine with anything, but it is the highest degree term of 2. I will write it first. Negative 2p plus 6p is positive 4p, and 4 minus 8 is negative 4. So this is a simplified version. That result is a quadratic trinomial, which I think we have to name this thing in a second. But the degree of this thing is 2, being a quadratic. Classified by the number of terms, I'll do you one better. I'll just say that it has 3 terms. So therefore it is a quadratic. That's by the degree. Trinomial by the number of terms. And we do a lot of things with trinomials, especially factoring. But there's that guy. Okay, that's number 1. Number 2. 9c to the 6th minus 5b to the 4th, and then minus this other guy. So they do the subtraction first, which is, listen, it's a test. They can put anything in whatever order they want. But when it comes to me talking about it or teaching it, the subtraction becomes harder than the addition, at least depending on what the problems are. Okay. So this problem, we can write this without parentheses so that this is exactly written as you see. But here we subtract by subtracting the positive, 4c to the 6th, and subtracting the negative becomes addition, 5b to the 4th. Now, I'm already seeing negative 5b to the 4th plus 5b to the 4th becomes 0, so I'm just going to get rid of that. You're down to one single term. It's 9t to the 6th minus 4c to the 6th, which is 5c to the 6th. That is standard form. That is simplified. That is all. It is a 6th degree polynomial with one term, which makes it a 6th degree. They really want me to say sextic again. 6th degree monomial. 6th degree monomial. One term is a monomial. And then number 3. Let's leave that up there while we work. Number 3. 4s, so this is the addition. 4s to the 4th plus, okay, this one's different. Plus 2st plus t. Plus 2s to the 4th minus 2st minus 4t. Okay, and they could have been very rambunctious with this. They kept it pretty mellow. You can see things that will likely combine, things with s and t combined, just the t's combined, and the s to the 4ths combined. So everything here is going to have something to combine with. But let's write it without parentheses just to see it clear as day what's going on. Now, addition is not going to change any of the signs as they were. Adding a positive is still a positive. Adding a negative is still subtraction. So just like that, but just seeing it without parentheses is a nice clarity moment. 4s to the fourth plus 2s to the fourth will give us 6s to the fourth. Now I want to put my st terms first because they would be of degree 2. 2st minus 2, oh, they cancel out. 2st minus 2st is 0, so those are gone, and they do combine to be gone. And t minus 4t is negative 3t. But st would have been degree 2, and t would have been degree 1, so for standard form's sake I would have put it first, but it doesn't seem to exist anymore, and that's the simplified result. The degree is 4, being s to the fourth power. It is 2 terms. So this is known as a quartic, not quadratic, but a quartic binomial. Binomial being the number of terms, and of course that's what they ask for. I'm giving you a little more information because I feel like it's important to say what those words are. Specifically the word quadratic or the word linear. I think those two have really shown up for me to talk about when I'm teaching something, more importantly. And that was stuff out of section 2.1. I don't know if that's the end of 2.1 material, but that is something that we saw. Okay, find the product. So numbers 4, 5, and 6 look very much, I take it back, numbers 4 and 5 look very much out of section 2.2. And then number 6 looks out of section 2.3. I'll mention why in a moment. We have h minus 5 times h minus 8. We can distribute and multiply this out by means of FOIL. Each term in one polynomial multiplies with every term in the other polynomial. Or you multiply the first, outside, inside, and last terms together, and you combine like terms. H squared minus 8h minus 5h plus 40. That is negative 5 times negative 8 that is occurring there. So we get that. And now that is h squared minus 13h plus 40. Another quadratic trinomial. Not that they're asking for that, but there is standard form for number 4. Number 5, more of the same, just excuse me, a little bit bigger numbers with the distribution. So 2w minus 3 times 3w plus 5. Now I'm actually not going to show any work this time. I'm just going to go from here to the answer just to remind yourself of when we play factoring to try and get to this, how important it is for us to look at that outside and inside together, or how I'm going to be talking about it. So 2w times 3w is 6w squared. 6w squared. The next two terms are going to have a w in it, 10w minus 9w. In my head, I'm just thinking 10 minus 9. I know they will combine here. So 10 minus 9 is 1. You're left with 1w. And then negative 3 times 5. Remember, it's a negative 3. Negative 3 times 5 is negative 15, and that is the result. So there's a mental process that's gone on there, but when it comes to me playing with factoring and stuff like that, foiling is also played with, and that's what I would get to. Now, number 6, listen, you could treat number 6 as much as these other problems as you'd like. You can foil it to your heart's content. There's nothing wrong with that. But when it comes to what you've learned possibly out of section 2.7 and recognizing a difference of two squares and how it's factored, this is that factored form. So when you distribute this thing out with a plus b times a minus b involved, this does indeed distribute to a squared minus b squared. Z squared is exactly that, and 11 squared is 121, which is the answer. See, when you FOIL, no, you don't just multiply the first terms and last terms. However, the middle terms canceled. Negative 11z plus 11z is 0. They're gone, so I'm recognizing a difference of two squares for what it is, because obviously I'm going to need to know that when I factor things later. And that is number 6. Number 7, explain how you can determine whether a polynomial is a perfect square trinomial. That's also out of section 2.3, or maybe a little bit out of section 2.7. It's kind of a combination of both. I think 2.7 it applies more because we got to recognize what it is. So explain how you can recognize that. Let me kind of write out what this scenario is. When you do a plus b quantity squared, it'll become a squared plus 2ab plus b squared. This is known. I'm going to call this a 2.7 problem because I don't believe they even say the phrase perfect square trinomial until you hit 2.7. But that happens, and a minus b quantity squared equals a squared minus 2ab plus b squared. So these are examples of perfect square trinomials. These are PSTs. They are trinomials. They are the results of squaring a sum or a difference like this, and this is what you get as a result. Whether they're numbers or variables, it doesn't matter, but those a and b are specifically in reference to whether you have x's and 4y's and things like that. But how can you tell? What is the appearance? The first and last terms. Now, this is assuming, well, hold on, assuming all GCFs factored. right? Because you can factor them out first before. But assuming all GCFs are factored out, the first and last terms are positive perfect squares. They do have to be positive of values, and the middle term is double the product of those two values. Now, keep in mind, one of those values, actually both of those values could be negative, but the fact that if I call one of them subtraction, then I suppose what we're saying is that one of those values is technically negative. The subtraction comes from the fact that we're multiplying a with negative b. And that's what we get. That's what it looks like. We're probably going to run into some that have them, so I'll call it out when I see it. But there are so many perfect square trinomials under the sun that, not even funny, right? We could get to those. Number 8, is 18 a polynomial? Explain your reasoning. The number 18. Yes. So I'll type out why, and I'll kind of get into it. Yes, 18 is a polynomial. Now here's why. Besides the fact that I would see a constant appear in polynomials, if you look at I'm looking at number 1 right now. We had 4 and we had 8 in things that we were talking about with regard to polynomials, and 4 minus 8 was negative 4. Constants can exist in polynomials, but why? Polynomials consist of terms, or in this case, monomials, right? I'll just say terms, but monomials fall under this definition, right? Polynomials consist of terms or only one term, such as a monomial. I'll say that. Whose variables contain whole number exponents. Now, I don't remember or recall what kind of definition the book uses. If they mention whole numbers, that's great, because I'm going to go ahead and bring about what that is. So 18 could also be written as 18x to the 0 power. And I bring up x just as a generic variable. I can throw in y to the 0 power and z to the 0 power and stuff as well. But here are the points I want to make with regard to that. X to the 0 power is 1. X to the 0 power is 1, and 18 times 1 is 18. So the reason I bring up the 0 is because 0 is a whole number, and it satisfies this condition that the variables would have whole number exponents. That's why with all the polynomials that you see, you always see it to the third power, to the second power, to the first power, or well, it won't say to the first power, but just like p or x or q. And then with a constant, that's to the 0 power, and that still satisfies it, as 0 is the smallest whole number. You see, negative 1, negative 2, negative 3, those actually aren't whole numbers. Those are just negative integers. And when you have something raised to the negative first power, keep in mind that if I had 18x to the negative first power, that'd be the same as 18 over x. And you don't see these in polynomials. This is known as a rational function. Anyway, I'm over teaching, but the problem is asking me to teach. That's why it says explain. So that's fine with it. But I just wanted to bring up that's how it would be satisfied, and that seems to work. Obviously, 1/2 is not a whole number. Or the square root of 2, because its simplified version is, 1.4 something. So this is something that seems to fill in with that. Constants do exist with it. It's totally allowed. This also explains how I should have mentioned this. This also explains how this would be a degree 0 term. So degree is 0 because the variable's to the 0 power. Or whatever variables you put in. But that's number 8. That's a 2.1 question. That goes back to definition of polynomials in a sense. So looks like they are mixing and matching. Okay, let's go to number 9. Factor the polynomial completely. Of course, they put s's with 5s, but I have s squared minus 15s plus 50. Now, this is out of section 2.5. There are no common factors, which is something I should always seek first, and especially now that we're in a chapter test, nothing's in a vacuum anymore. Anything is fair game. They won't tell you when something's a special case or not. They won't tell you something has a GCF or not, so that's good. What I wanted to bring about is something that I probably did not cover as much while teaching, and just saying that I don't treat the 1s squared technically any differently than if it was a 2 or 3 or 4, other than we ain't doing diamond talk. But what I can do is start off by saying if it's factorable, it would start to look like s times s. With a positive product and negative sum, I know both of these will be minuses. But here's the good news, that when I FOIL this thing out, the outside plus inside, these numbers do represent the sum that makes 15. I don't even have to worry about what I'm multiplying s with when I test it, though I do have to in problems like like number 11, looks like that's something I'll have to worry about. But I am finding factors of 50, such as 5 and 10, 25 and 2, 50 and 1. I don't think there are any others. If there are, let me know. But I'm going to start with 5 and 10, and that seems to be the one. 5 minus 10, negative 5 minus 10 is negative 15. In previous times, and in future times as well, you'll hear me say what two numbers multiply to 50 and add to negative 15. You test and find those values, then you insert them in. Either way works. But when you see me do a problem like number 11, I'm going to kind of get more into the nuts and bolts of, well, you got to first write with this because you need to test some values out in your FOIL process. But that's the answer. An answer. Or s minus 10 times s minus 5. Number 10. We have h cubed plus 2h squared minus 9h minus 18. We are going to factor this completely. This is a factoring by grouping case. This is in standard form, which is good. I'm going to pair off, two sets of factors. What was I going to say? Us teachers in my department have been talking about whether or not we should do this in full with IM2 students because this is also taught in IM3 in a big way. Anyway, I factor out an h squared out of here as a GCF. It's the greatest common factor. You're left with h plus 2. Negative 9, negative 9h. Negative 9 is the leading coefficient of this set here, so I factor that out, and you're also left with h plus 2. H plus 2 is a common factor of both sets, and when you factor out h plus 2, here you're left with h squared minus 9. And this has to call to your attention. H squared minus 9 is a difference of two squares. We are not done factoring, as they ask us to factor completely. H squared minus 9, difference of two squares, is h squared minus 3 squared, which factors into h minus 3 times h plus 3. So that's what we get out of that. And then h plus 2 still remains, and that is the final factorization or complete factorization of number 10. More than halfway done on the Chapter 2 test itself, number 11. Well, at least problem-wise. I don't know about content-wise. It looks like we get word problems after. Maybe I spoke too soon. Negative 5k squared minus 22k plus 15. Let's go. To begin with, there is no GCF as far as numbers or variables go, but there is as far as signs go. If I factor a negative out, or some people would say a negative 1, inside you're left with 5k squared plus 22k minus 15. As I say over and over, this not only makes the problem easier, but it is a required step to factor that negative out as far as getting an answer. Now we attempt to factor this. There's nothing that says that it is factorable. I'm going to make an assumption that it is and give it a shot. With a positive, negative product and positive sum, I don't know yet what's added or subtracted. Let me stick it this way for now. I need to find factors of 15 that when I FOIL, outside plus inside gives me 22. We can try something like 5 and 3, and I see where that can actually work. Notice that if I do try 5 and 3, I wouldn't put 5 here and 3 here, because this would lead to a common factor of 5 that never existed to begin with. So let's try 3 here and 5 here. If not, we'll try 15 and 1. But negative 25 through FOIL, that's negative 25 plus 3, which is negative 22. Now I need a positive 22. Don't look at this one, you got to look at this one. So I have the numbers in the right spot, but I need to change their signs. This needs to be a minus, this needs to be a plus. So that is the factorization of this portion. The negative that's factored out right there means this is the final factorization of this guy. 5 being a prime number really helped for me saying it has to be affirmed like that. And I did do it in a first test basis. If not, I would have tried 1 and 15. Would have noticed 5 times 15 is a little too big. And if that didn't work, then it couldn't have factored any further, but it did. All right, we're going to solve some equations on numbers 12, 13, and 14. Number 12 is set up for us to solve right off the bat because it is already factored. Factored means we have a product, and a product set equal to 0 is well on its way. We will use the zero product property. If n minus 1, this, times n plus 6, this, times n plus 5, this. If this times this equals 0, then either this equals 0. Let me do that again. Then either this equals 0, or this equals 0, or this equals 0. Simple solving from here, n either equals 1. Subtract 6 over, n is negative 6, and the last one is n equals negative 5. Next time I will not spend time showing the step above to go to this step here as far as subtracting or moving things over. It's just the opposite sign for those particular problems. Maybe not for all of them. Number 13. We have d squared plus 14d plus 49 equals 0. Now, I recognize something about this, and I'm going to call its attention. However, you can do this in more than one way. First of all, we do need to factor this to solve, at least in the scope. Until you hit chapter 4, you don't know other methods of solving. I would still solve by factoring regardless. But this is factorable. Not only is it factorable, it is also a perfect square trinomial. Before we jump to number 13 in full, let's look back at how can you determine whether a polynomial is a perfect square trinomial. Remember, you don't seek them. They need to call your attention. Is the first term a perfect square? Is the last term a perfect square? Is the middle term double the product of those two values that we squared? In this case, we square 1d to get d squared. We square 7 to get 49. And this, the question is, are we doubling 7d, d times 7? Are we doubling 7d to get 14d? The answer is yes, and that's the recognition. We have a squared plus 2ab plus b squared. Now, I didn't factor. I'm just calling attention to the fact that this is a squared plus 2ab plus b squared, where a is d and b is 7. So this does factor into a plus b quantity squared, d plus 7 quantity squared, and that is the factorization of that. Now, we're not done, but factoring helped create a product for us, or something times itself. The only thing we can square to get 0 is 0. Therefore, d plus 7 has to be 0. Therefore, d has to equal -7. One single answer and a repeated root, but that is the solution. It's the only value that will work in that case. And that is number 13. As a perfect square trinomial, a 2.3 question. Excuse me, a 2.7 question. Number 12, by the way, would have been out of, I forgot to mention where these would have been out of. Number 9 would have been out of 2.5. I think I did mention that. Number 10 would have been out of 2.8. Number 11 would have been out of 2.6. Number 12 would have been out of 2.4. Number 13 would have been out of 2.7. So they are covering the gamut here. I would imagine you would see number 14 out of 2.8 just based on the fact that you have a GCF first. Otherwise, this kind of looks also like a 2.6 problem. But we have 6x to the 4th plus 8. I would have taught it in 2.4. 6x to the 2.6. 6x to the 4th plus 8x squared equals 26x cubed. In order to solve this thing, we got a couple things to do here. Before factoring anything, we have to set it equal to 0. The zero product property necessitates 0 is what we get out of the product. But then we create a product after that. I'm going to subtract 26x cubed from both sides and put it in standard form so it's right in the middle, right there. Set equal to 0, now we go to factoring. And there's more than one stage of factoring for this kind of problem. It starts with a GCF. I can factor at least a 2 out of here. Number-wise, I believe that's the most I can do. And there are a couple of x's we can factor out, an x squared. So now we're going to be dealing with 3x squared there. So 2x squared times 3x squared is 6x to the 4th. Divided by 2 is -13, and that's an x. And 2 times 4 is 8. Yeah, 2 times 4 is 8. And that's what we'll hit there. Assuming they're letting us solve by factoring, I'm only going to have to assume that's factorable as well. So 2x squared here. I know I'm getting a 3x and x showing up there. This equals 0. Positive product, negative sum means minus and minus. 4 is either 4 times 1 or 2 times 2. I'll tell you what, it's not 2 times 2 because 2's would give me an even sum result. If you've dealt with me before, you know what I'm talking about. So it's either 4 and 1, which this won't be. -3 minus 4 is -7, not -13. Or it's 1 and 4. 1 and 4 where we get -12 minus 1, which is -13. See, knowing I had to get -13 means I had to get my numbers big kind of fast. So multiplying the big number with the big number would probably help us out. And there's the factorization. We're still not done. We are solving either 2x squared equals 0. Now this part might be a little confusing for people when it comes to solving if you haven't solved by other means. Remember x squared, well, first of all, if I divide by 2, I get x squared equals 0, which is still a product, right? We go back to the previous problem, literally. D plus 7 times D plus 7. This means x times x, which is its own set of something times itself is 0. You can either split it and understand that either x equals 0 or x equals 0, or the only number that you can square to get 0 is 0. So if x squared equals 0, then x equals 0. It's a whole way of saying what number do I have to plug in here to get 0? 0. But there are other values we can plug in to get 0 as a whole result, right? Obviously for this one, it would be x equals 4. This last one, you might want to write out the 2 steps. If 3x minus 1 equals 0, you add 1 to both sides, and then you divide both sides by 3. And we get 1/3. Do not round it. Do not write a decimal version of that. That's exactly what you would want. 3 solutions, one with a repeated root. That is number 14. Okay, so that would have come out of section 2.8 in the book, but like I said, it's still 2.6-ish. Number 15, the expression pi times r minus 3 quantity cubed represents the area covered by the hour hand on a clock in one rotation. Okay, let's see where this is going. Where r is the radius of the entire clock. Okay, I understand that. Write a polynomial in standard form that represents the area covered by the hour hand in one rotation. So they're not asking you to do anything with the information other than expand what that is. But to show you what they're talking about, I do want to draw it out, because what if they asked us other questions? They won't, but I'm just wondering. So let's say this is a clock, okay, and it's got your numbers and all that, and you have some sort of hour hand. Okay, let's say that's the hour hand. Maybe it's a little short. Now, notice that they mentioned that r is the radius of this entire thing. So that distance is r, but this distance here is r minus 3. I guess which means that this distance right here is 3, because you got to subtract 3 for it. So that's the first part. That's where that comes from. And then they talk about the area of the hour hand after one rotation. See, if this thing does a rotation, it goes, and then it covers basically an imaginary circle. Everything that the hour hand touches by the stick, if you will. I don't know what you would call it. A stick. I don't know. But everything covered by that would have hit this whole area right there. Now, the area of a circle is pi r squared. But your r, in this case, is r minus 3. So our area is pi times r minus 3 squared. And that's where that's coming from, just for an explanation. They want us to write a polynomial in standard form that represents the area covered by the hour hand in one rotation. This is the factored form. This is the factored form. So let's get the standard form. Let's expand that. Pi is going to, remember, I can't distribute pi into here. This is being squared first, order of operations. So we have to go ahead and expand this. And this would be a 2.3 question, because they have r minus 3 squared. That means you practice expanding this into a perfect square trinomial. It's r, we square r, we double the product of these two, negative 3r doubled is negative 6r, and then we square 3, or negative 3, and we get positive 9. Pi is multiplying by that. Well, this is standard form-esque, but there are still parentheses multiplied by pi. Now you distribute in the pi here, and you get pi r squared minus 6 pi r plus 9 pi. That is the area, and that's the answer. So there's your standard form. I got your standard form right here. Number 16. A magician's stage has a trap door. No, they're magic. They have no trapdoors. That's just the illusion in and of itself. They want you to think. They need that trapdoor. The total area, okay, so let's see what we're looking at actually. Let's copy and paste that. Give me 1 second. Because I don't want to redraw something if I don't have to. Whoops, put it in the wrong spot. Okay. All right, the total area, A, in square feet of the stage can be represented by x squared plus 27x plus 176. Write an expression for the width of the stage. Okay, so we have, but see, I guess the trapdoor doesn't count as anything here, so that's fine. X squared plus 27x plus 176. Now my goal, I still haven't looked at what that width is. I can tell something's labeled down there, but my goal is to factor this. I'm just going to look at that number again, 27. Okay, so our goal is to find factors of 176 that add to 27. Now, I don't know what 176 all divides by. I guess 16 is one of them, which actually might be part of the answer. Actually, I think it is. Because 176 can divide by 1 and 2, not 3. You can divide by 4. If it divides by 4, it gets 44. 4 plus 44 isn't 27. 5, no. 6. Yeah. No. 6, no. 7. No, because 175. 8, yes. 22. 8 plus 22 is 30, getting a lot closer. 9, no. 10, no. 11, yes. 16. So you divide by 11, you get 16, and 11 plus 16 is 27. So this factors into x plus 16 times x plus 11. Now, they ask for the width. The reason why I said I didn't want to look at this thing yet, what was x plus 16, is because they've provided one of them for us. But I wanted to factor with plausible deniability, saying I didn't want to know what one of the factors was beforehand. That being said, you can totally look at it and use it to help your factorization. But if practicing factoring is a part of what you want to do, then you got into that. But that's the length. So this is the width. The width was x plus 11. And the reason I kind of bring all that stuff up is because I was saying, why would they help us on the problem? Why would they give us one of the answers to the factorization with the thing? But I guess the reason is because they want us to determine the other guy. If that's the length, then this is the width. And so they need to tell us one of them, I guess. There are other ways to determine what would have been the width or not, but that's it. Part B, write an expression for the perimeter of the stage. So if that was x plus 16 there, this is x plus 11, and it's rectangular, then the perimeter is going to be identified by doubling x plus 16 and doubling x plus 11. There are two x plus 16 down here and up here, two x plus 11s on the left and on the right. So that'll be perimeter. You get 2x plus 32 plus 2x plus 22, which is 4x plus 54 feet. Units, folks. Let's get them. Part C, the area of the trap door is 10 square feet. Find the value of x. So area is 10. And we have dimensions of 2x by x plus 1 half. So 2x times x plus 1 half. When I get that in total, that's going to give me my area. I can distribute 2x times x and get 2x squared. 2x times 1 half is 1x. So multiplying them out, that equals 10. Now I have a polynomial, a quadratic, at that if I set equal to 0, I can solve by factoring, assuming it's factorable. And of course, I don't think they'd give us this problem if it wasn't. So getting that lined up, there's no GCF, but I know that if factorable, it's going to look like some version of this. Let's find out factors of 10 that'll work out. I can try 5 and 2, but if so, I got to put the 5 here and the 2 here, not the other way around. I do get negative 4 plus 5, which is 1. Happy accident. I got it. 1 is what I wanted right there, right? So that's the factorization. When I set these equal to 0, I will get x equals 2 as one answer. And just subtract 5 divided by 2, I'll get negative 5 halves as the other answer. When it comes to them asking us for the value of x, I'm not going to take this one because using that one means that I would do 2 times a negative or a negative plus a positive, what would still lead me to a negative. I need to use the positive version of the answer. So x equals 2, or in this case, probably, I don't think you have to say 2 feet because feet are already used in the expression. So x equals 2, that's the one that they want. And part D, I'm going to go and move to the other page and just paste that image in again. The magician, this is 16D. The magician wishes to have the area of the stage be at least 20 times the area of the trapdoor. Does this stage satisfy his requirement? Explain. So we have expressions for the area of each of these. I don't know which one we'd prefer to look at, whether it's the expanded polynomial. I'll go ahead and do the expanded polynomial. So we have x squared plus 27x plus 176 for the whole guy. And the small guy, we had 2x squared. Well, you know what? The other guy, we have 10, right? We already know that the other guy is 10. Oh, wait. Does that still apply to this? Oh, 20 times the area. I apologize. I was thinking they meant substitute 20 for the answer. Okay, let's look more at what 20 times the area means. Does the stage satisfy his requirement? Explain. So we have, let's see, let me go back on this. How are we going to determine this without using polynomial division? So I have 2x squared plus x. Okay, that equals 10. Let's see if there's a way. Let me think on this a little bit, on what they would have us do. Because you guys aren't going to be dividing in any sort of way that we would have done before. Area of the stage be at least 20 times the area of the trap door. Oh, I missed part C. No, I didn't. You know what? Let's just substitute a number. So here's the idea, right? We have x squared plus 27x plus 176. This is the area of the stage. And now we have the area of the trap door, which was... Oh, they said find the value of x. I'm sorry. We did find a value of x. Okay, the area of the trapdoor is 10. We found a value for x. I totally forgot that. What did we get? 2? We got 2. Okay, I thought these problems were treated in isolation, in that we were solving for x for a different thing. I'm like, well, it's 10. Can we use that? Okay. 2. X equals 2. So the area of the stage, we're going to go ahead and substitute in 2. 2 squared plus 27 times 2. This is what happens when you do this on the fly. Plus 176. We got to see if this number is at least 200, because 10 times 20 would be 200. 2 squared is 4. 27, yep. 27 times 2 is 54, and 176. 54 plus 176 is 230, plus 4 is 234. So 234 is greater than, they said at least, greater than or equal to 10 times 20. Yep, we get 234 is greater than or equal to 200. These are in square feet. As far as a comparison goes. So the magician wishes to have the area of the stage be at least 20 times the area of the trap door. So yes. Now keep in mind, I still don't know if the area, so yes, because reasons, as you can see up here, I still don't know if they mean the staging area would include subtracting out the trapdoor area. But even if you did, 234 minus 20 is still more than 20 times 10. So 214 is still more than 200. So it would still be a yes by those measures. Anyway, what I was going to say here was that I could have substituted any number in for x. No, I don't know if that compares by 20. I wonder if I substituted anything for x, would it still apply if I substituted 1 or 10 or whatever, no matter what? Would have that still given me 20 times more? I'm not sure now. Not sure. But with x equaling 2, it does. Okay, now that took some time out of my stuff. Let's move on to number 17. Write a polynomial equation in factored form that has 3 positive roots. Okay, positive roots are opposite of your factored form. If I have x minus 2 times x plus, minus 5 equals 0, then x equaled 2 and x equaled 5. Notice those positive roots you have right there? Look at how the factors appear. They are subtracted out because we have to add them over when set equal to 0. So, I mean, listen, I can write anything that's 3 positive roots as long as they're whatever. I can do 2x minus 7 times x minus 3, as long as I have minuses here, times x minus 10. They said write the equation in factored form, so I think I really need like a y equals here. And they said factored form. They didn't say distribute, so that's it. Kind of open-ended. I don't know what that would go into. I guess section 2.4. The one before that would have probably been section 2.5. Number 18, you are jumping on a trampoline. For one jump, your height y in feet above the trampoline after t seconds can be modeled by y equals negative 16 t squared plus 24t. How many seconds are you in the air? So they're asking, so you bounce off the trampoline once you leave it, or sorry, your feet on the trampoline is at 0 feet. Once you leave it, you go up in the air. This would be modeled by a parabola and a graph, but the point is that from time 0, which you'll actually, when t equals 0, you're actually still on the trampoline. We're going to find that is one of the answers. But from time 0 to time unknown is how long you are on the trampoline from y equals 0 to y equals 0. I want to substitute 0 for y in this equation, and I want to determine what value of t gets me 0 for y. It should be 2 values. One of them is going to be 0. I can factor out a negative 8t from here, and I'm going to be left with positive 2t minus 3. Now, this is where if negative 8 times t equals 0, t equals 0 is one of the answers. And that's totally valid. We need that number and that information for this. And then if 2t minus 3 equals 0, we add 3 and divide by 2, you'll get 3 over 2. Now, as far as time goes, generally we start to put this into a decimal at that point. At time 0 is what is the last time that you're on the trampoline before you go in the air. And then you hit the trampoline again at t equals 3/2, which is 1.5. So the difference between 0 and 1.5 is 1.5. You are in the air for 1.5 seconds. I guess that's reasonable for a trampoline. You can bounce up a little bit. That totally works. And then number 19, before we hit the cumulative assessment, these are together. A cardboard box in the shape of a rectangular prism has the dimensions shown. So we have x plus 6 as the length, x minus 2 as the width, and x minus 1 as the height. Write a polynomial that represents the volume of the box. Now, generally in these cases, I'm going to write a y equals, v equals, v would represent the volume. Generally in these cases, they also mean like expand it out. Like actually multiply these things out, x minus 2 and x minus 1. I think. Well, you know what? Maybe we don't have to, but we are going to do it for part B. This is an expression, though. That's length times width times height. That works. I'll go and expand it out here because I have to later anyway. So let's see. When we do this, we have to be careful with our foiling stuff or with our distribution. We can only do one at a time with ease. So I'm going to begin by multiplying these ones out, and I'm going to have x squared minus 2x plus 6x is plus 4x, then minus 12. And I'm going to multiply that with x minus 1. I like to write this one first. Sorry, I just do. Now, x multiplies with x squared, 4x, and negative 12. And then negative 1 multiplies with x squared, 4x, and negative 12. That's a distribution of those. And when you combine like terms, we get x cubed plus 3x squared. I'm sorry, this should have an x in it. Plus 3x squared, because I said negative 12 out loud. That's what I did. Minus 16x plus 12. Okay, so that is, and I just want to make sure all looks good. Plus 4x squared minus 12. Okay, I think all is good. Just triple check that. It's all looking good. Okay, so there's an answer to the volume bit. Now, part B. The volume of the box is 60 cubic inches. What are the length, width, and height of the box? So now we set this guy, whether it was the factored form or then expanded to standard form, equal to 60. And at this stage, we are now going to solve by subtracting 60 over, setting this equal to 0, and then factoring the new, whatever comes from this. 12 minus 60 is negative 48. This is a totally 2.8 kind of question as far as how big it got, in that we can factor by grouping. X cubed plus 3x squared can factor in x squared out, and you are left with x plus 3. Negative 16 can factor out of this bit here, and you are left with x plus 3 once again, which is kind of the goal. You need that, because as x plus 3 factors out here, you'll now have x squared minus 16, which is a difference of 2 squares. That is x plus 4 times x minus 4, and then times the x plus 3 equals 0. And as is generally the case, there's only going to be one answer that really applies well. It looks like x equals 4 will be it, because these other answers are negative. So we will eliminate those ones. We'll use x equals 4 for this, and then they ask what are the length, width, and height of the box. We are going to substitute 4 in for where we have the length is x plus 6, 4 plus 6, which is 10 inches. The width is 4 minus 2, which is 2 inches. And the height is 4 minus 1, which is 3 inches. And 10 times 2 times 3 is indeed 60 cubic inches, the way that we wanted it. So that, excuse me, that wraps up, RIP headphone users, that wraps up the Chapter 2 test portion of things. I'm now going to go to the cumulative assessment, which should probably cover Chapters 2 and 1. And if memory serves correctly last time, they were kind of multiple choice questions or things that would go a little bit faster. I hope to finish within the hour on 9 more questions. So let's see what we have here. Number 1. Classify each polynomial by the number of terms, then order the polynomial by degree from least to greatest. Okay. So on this one, for whatever reason, they want you to write in reverse standard form. So for this here, Classified by number of terms. Okay, this time I'll just do number of terms. It's a monomial. And then as far as the reverse standard form, RSF, I'm calling that reverse standard form. It is still negative 4x cubed. It is a single term. So monomial and then that. Part B. So this one's not really multiple choice, but it's multiple. It's multiple problem. By degree from least to greatest. Okay, so 6y minus 3y to the fifth. Number of terms, binomial. That's its name, 2 terms. Reverse standard form, we are already there. Degree 1 and degree 5. So 6y minus 3y to the fifth. I don't know why they're asking us to do least to greatest. This is not generally an expectation. There's no added benefit to my knowledge of seeing it this way. I hope this doesn't just screw you up a little more so. C squared plus 2 plus c. I think they're saying, can you follow instructions? 3 terms is a trinomial. Reverse standard form would have the degree 0 term first, which is the constant. Normally it would be c squared plus c plus 2. Now it's 2 plus c squared. It's already messing me up as well. D, we have negative 10d to the fourth plus 7d squared. You can see they are allergic to saying quadrinomial ever. I don't see any 4-term ones here. This is once again a binomial. From least to greatest degree, we are going to have 7d squared, reverse standard form. 7d squared minus 10d to the fourth. Come on, I want to finish in the hour. Part E, negative 5z to the 11th plus 8z to the 12th. That is a binomial, once again, 2 terms. And it is already in reverse standard form of negative 5z to the 11th plus 8z to the 12th. And lastly, part F, we have 3b to the 6th minus 12b to the 8th plus 4b to the 4th. This is 3 terms, a trinomial. By the way, nothing could combine, and if something could, then you'd reduce the number of terms. That's how it would look. In reverse standard form, let's find the smallest degree. Looks like that is degree 4. So we got 4b to the 4th, and then degree 6 and degree 8. So plus 3b to the 6th minus 12b to the 8th. And there you have it. Kind of a weird question. It's a little bit of a weird duck. Number 2, which exponential function has the greatest percent rate of change? So this is out of chapter 1. So looking back into what this has to do with, so 2, it's has the greatest. There are 4 options, A, B, C, and D. So in part A, not part A, in selection A, we have f of x equals 4 times 2.5 to the x over 3 power. Okay, I might need a calculator for this, it looks like. Now, 2.5. Now, by the way, it says greatest percent rate of change. It didn't state which direction. I assume greatest, though, means positive would be higher than negative. So let's hope that there's not a negative one that is larger than a positive, and I have to pick and choose. Otherwise, I'll talk about it. But the 2.5 here is actually being raised to the x over 3 power. X over 3 is the same as 1/3 times x. Keep in mind that. So this is to the 1/3 power all to the x power like that. That's important because we're looking at 2.5 to the 1/3 or the cube root of 2.5. That's how you do that. So the cube root, I'm going to do this on my phone, I guess. So sorry about this. 2.5 to the 1/3 power. I didn't expect to use a calculator, but I forgot about this. 1.3572. I mean, it goes for a while, but I'm going to put 1.3572 to the x power. It's important because this is your percentage change. This is 1 plus 0.3572 So which means this is about a 35.72% change. So that's A. B. We have a table, x and y, or g of x, where from 0 to 1 to 2 to 3 to 4, hopefully it's a constant change, otherwise we'll have problems. This goes from 8 to 12 to 18 to 27 to 40.5. What are we multiplying going from one value to the next? Common ratio, if you will, that b value that we're multiplying by. 8 times b is 12. 12 times b is 18 and all that kind of stuff, right? We multiply by the same value over and over. At least that's the assumption. I mean, I can tell that, yes, that is what we're doing. But we divide 12 by 8 to figure that out. Or 18 divided by 12, or 27 divided by 18. And assuming it's not rounded, it doesn't look like it is, 40.5 divided by 27. They all get you the same value, 1.5. 1.5 is 1 plus 0.5. And 0.5 added represents a 50% change. 50% is more than 35.72%. So far, this one is winning. B is winning. C. You see this graph that goes from, look at the scale. You see this graph that goes from, let's write this one out as a table. X and Y. We have, it's really about the Y values because X just goes up by 1. 0, 1, 2, 3. I can totally tell that, so they go by every 3. So 1 is at 3, 2 is at 9, 3 is at 27. Even if you didn't know what this one was at, you can tell that you're multiplying by 3 each time, times 3. So divided by 3 here, you would get 1. And it looks like it's 1/3 of the way up on that scale. So if your B is 3 this time, that represents 1 plus 2, which is a 200% change. Remember, times 3 is a 200% increase. So that one's bigger. The biggest so far, I should say. And lastly, D, I'll just fit it down in this set. An exponential function, J, models a relationship in which the dependent variable is multiplied by 6. For every 1 unit, the independent variable increases. The value of the function at 0 is 2. So this equation would be, and by the way, this equation would have been y equals 1 times 3 to the x power, or 3 to the x power. This equation, the at 0 is 2, that's your y-intercept, is your a. So 2 times multiplies by 6 each time, in which the dependent variable is multiplied by 6. For every 1 unit, the independent variable increases. That's a 6 to the x power. This means your b value is 1 plus 5. That makes it a 500% change. So these only increased over time. It will be D that ends up being the answer there. It just gets larger and larger as you go. None of them were negative. It looks like the percent change just grows, and that's what we're going to get. 500% change is the largest one. Did I answer that correctly? Which exponential function has the greatest percent rate of change? D. Okay. Yeah, we won't be able to finish within the hour now that I realize these are kind of slower questions for cumulative assessment. But hey, they got to test you. Number 3. Find the x-coordinate of the points where the graph of f of x crosses the x-axis. So, they give us options, but I'm not going to sit around and substitute negative 24 x squared minus 2 and all that kind of stuff. Where it crosses the x-axis is where, it's a weird version of multiple choice, I guess. It's going to be 2 answers. It's where y equals 0. So you said, so this would have been out of section 2.5. This is where y equals 0. We factor this thing. This factors into x minus 6 times x plus 4. Sorry, I'm going faster on that. And then you get the answers x equals 6 and x equals negative 4. These are also the x-intercepts. These are the points, the values of x, where they would cross the axis. So what are your answers? Those 2, 6 and negative 4. Not negative 6 and positive 4, but those 2 right there. They did ask for the x-coordinates, by the way. Okay, number 4. The table shows your distances from a national park over time. Okay. Write and graph an absolute value. Write and graph an absolute value function that represents the distance as a function of the number of hours. Okay. So I'm going to begin with the graph on this. It's not going to be a 2-scale version, like a beautiful one, but we go 1, 2, 3, 4, 5, 6, 7. And this goes up to about 200 something. So we'll go, I guess 50, 100, 150, and 200. 50, 100, 150, and 200. All right, let's pull out what we can here. We got 195s at 1 and 7, so really close to the top there. Boom and boom. And then at 4, we have 0. So all the way down here. Listen, I'm going to draw a straight line for now, and then I'll match up what I think would kind of be appropriate for this afterward. But let's go ahead and give that a different color. How about green? Okay, so we got a green. Whoops. Hold on. Make that green as well. All right, so we got a green graph modeling this function. So clearly we're referring to a vertex. And I knew this went this way because they called it an absolute value. Now at 2, they have 130. So that would be somewhere between 100 and 150. That makes sense. And at 6, they also have 130. At 3 and 5, they have 65, which is probably closer to 50, kind of like that. And that works out to me. Okay, so there's the graph. Okay, writing this thing, you have the vertex at 4, 0. That's the minimum. This rises and runs a certain amount. It's a rise of 65 every time it runs 1. I mean, you can see that in the information as well, but I think the graph is a nice version of reminding you how a graph is made from the equation or an equation is made from the graph. In this case here, it would be y and x. So y equals slope of 65, 65 times the absolute value of, and we do x minus 4, and then plus 0. You don't really need that part, but that would be the equation that models this thing. Hours and distance traveled in miles. Or distance from a national park over time in miles. I guess you go to the national park by hour 4 and then you leave it afterward, which is what's happening there. Number 5, which function has a steeper graph? F of x equals 2x minus 3, or the inverse of f. Explain your reasoning. By the way, number 4 would have been out of section 1.1, very first section in the book. Number 5 is out of section 1.3. And we'll see if over time when we do cumulative assessments, if I remember sections by number. I probably will, because I lived in the section for a while. Okay, so f of x equals 2x minus 3. Now the inverse of this is if you swap y and x. So taking the inverse is swapping x and y. Remember, y means f of x, so I just rewrote it like that. I swap these, and let's solve for y again, because I want to know what that slope is. I add 3 to both sides, and then I divide both sides by 2. I'm going to get y equals x plus 3 all over 2, but I can also rewrite that as the inverse here, the inverse of f, that's literally what they asked for, and I can divide them separately by 2. X divided by 2 is 1/2 of x, and 3 over 2 is plus 3/2, like that. Okay, now, 1/2 is the slope of the inverse, so that guy is 1/2. The original was 2. 2 is a steeper slope than 1/2. Even -2 would be a steeper slope than 1/2. It would be going down 2 and over 1, but that's still steeper. So the original function has a steeper slope. The original function, what they say, steeper graph, has a steeper graph. Function, but it's all based on slope. Slope-intercept form. Got a text about a shipment. I should probably read that soon. But that's the answer. 4 more questions. That would have been out of, once again, 1.3. Number 6. Which expressions are equivalent to negative 2x plus 15x squared minus 8? Okay, first thing I'm going to do with this one is I'm going to factor on my own, which also means I'm going to rewrite this in standard form, and then we'll see if we find anything equivalent based on that. So standard form, I should say, is 15x squared minus 2x minus 8. Now, as you can see, the leading term is positive. There is no GCF as well, so nothing to factor to start with. Let's go ahead and keep moving forward. 15x can either be 5x times 3x or 15x times 1x. If you know me, I'm going to start with the 5x and 3x. I think it's more likely to be the answer, and I'm just going to work off of it. Now, 8 is either 8 times 1 or 4 times 2. However, because of the even sum here, I'm going to deal with 4 times 2. And I can place 4 and 2 in either one. Let's try 4 and 2 like this. 1 positive, 1 negative. Let's go for it. Negative 10 plus 12 is positive 2. I need negative 2, but at least I have the right numbers. Let's go and swap that up. It's worth kind of testing all the other different things, but looks like that's going to be the result. Now, I haven't looked at any of the options yet, but that's the factorization that we have so far. So here are two different varieties of answers so far. Standard form, or whatever version they give us, and factored form. Whatever else they give us is either wrong, or I don't know what they're trying to give us as a result. So, what do they give us? Let's see. 15x squared minus 2x minus 8. Okay, that is standard form. So boom, that is equivalent and better, and that's a better looking version of it. 5x minus 4 times 3x plus 2. That is also the factored form like I just said. That does work out. Now, 3x minus 2 times 5x minus 4. That would have given you negative 12 minus 10, which is negative 22x, and it would have given you plus 8. That is not the factored form of it. And by the way, if my students, I'll do it for the next example. Let's see, I'll do it for the last example. But if my students give me an incorrect factored form, the immediate thing I'm going to show them is what it looks like when it's FOILed out. Why it's incorrect, because this number was wrong, because this sign was wrong, because you forced this number into it. So I'm showing them like that it's wrong. You can always double check your answer here. Like I'm going to double check this one. Will this give me it? No. 4 times 2 is 8. This gives me 10 plus 12. That's positive 22. That's not it. Plus 2x minus 8, it still has to be a minus 2x, so that's not going to work. So let's check this last one. Let's say you said, hey, I factored like this. Oh, you know what? This one's still correct. I'm sorry. This is a rewrite of it. So yeah, if you tried one of those other ones, I would have said no, because this becomes, 15x squared plus 22x plus 8. 15x squared minus 22x plus 8, and those wouldn't have worked. Okay, those are the equivalent ones. Number 7. The graph represents an exponential function. Yes, it does. Write the function, part A. So on number 7, we do have negative 1, 4, and then we have 0, 1. Now I'm sure that they have given ways for you to come up with this stuff. What we have to do though is find out from negative 1 to 0 on x when we go from 4 to 1 on y. Remember, don't say times 4 going this way, and definitely also don't say dividing by 4. You ask what you're multiplying by going here. Times some b. If 4 times some b equals 1, then that b is 1/4. You are dividing by 4, which is multiplying by 1/4. The a value is the y-intercept. The a value is 1. So as far as this goes, in y equals ab to the x form, this is y equals 1/4 to the x power. 1 times 1/4 to the x power. That is part A. A little messy, sorry. Part B, find f of 1/2 and f of negative 5/2. Okay, the first question would have been out of section, this section before would have been out of 2.6. This would have been out of section 1.6. This part B looks a little bit more like it would have been out of section 2.5. 1.5, excuse me. F of 1/2, we are going to do 1/4 to the 1/2 power. Now, raising something to the 1/2 power also means taking the square root of it. And the square root of 1/4 is the square root of 1 over the square root of 4, which is 1/2. F of negative 5/2 is going to give us 1/4 to the negative 5/2 power, which also is positive 4 over 1, or 4 to the positive 5/2 power. I should have said positive 4 over 1. 4 over 1, we flip it to the positive 5/2 power. Now that means we do take the square root of 4 and raise it to the 5th power. The square root of 4 is 2, and 2 to the 5th power is 32. Now see if that makes sense with these things. We see the graph at 1/2. 1/2 on x. I'm getting 1/2 on y. It looks like it. Negative 2.5 would have been here. Negative 1, negative 2, negative 2.5. Goes all the way up to positive this, positive big. 32 seems to make sense as an answer. Just seems to make sense. Okay, number 8. Which polynomial represents the product of 3x plus 1 and 4x minus 1? You have two options. You can either factor all 4 of these. Well, some of these aren't really factorable. Or the better option is you can distribute this and see which one this is. This would be out of section 2.2. 2.2. So we FOIL this thing out. We get 12x squared minus 3x plus 4x is plus 1x, and then minus 1. So which one is that? D. They sure like part D as the answers, or option D as an answer. Last question here is number 9. You are playing miniature golf on the hole shown. Write a polynomial that represents the area of the golf hole, part A. Write a polynomial that represents the perimeter of the golf hole, part B. By the hole, they don't mean the black circle. They mean the entire thing. Find the perimeter of the golf hole when the area is 216 square feet. Okay, so 3 different things. I'm going to go ahead and copy and paste this thing over. Let me try that one more time. Excuse me. Okay. Let's begin on part A. Find the area. Now the area can be broken up in different ways. I'm going to go ahead and kind of splice this down here where you have an x by x square, which is x squared, plus this x to the 4th times 3x, or x to the 4th, x plus 4 times 3x, which gives you 3x squared plus 12x. So your area comes from adding those two, x squared plus 3x squared plus 12x. So you get 4x squared plus 12x as your entire area. Part B. Perimeter of the golf hole. Perimeter is adding up all the lengths of all these things. These are x's, so is this. That's an x plus 4, so is this. This is 3x, and we have to take away an x over here, so that would be 2x. Normally I'd say 2 of these plus 2 of these and all that stuff, but because this length is cut off and this length is different, even though it's, well, technically 2x and x are added right there together. We could have used that, but that's okay. I'm just going to go ahead and add them all separately. Perimeters, x plus x plus x, those 3, I'm going to wrap around here, plus x plus 4, plus 3x, plus x plus 4, plus 2x. And you can see there are better ways I could have cleaned that up for sure. Okay. 1, 2, 3x, 4x, 7x, 8x, 10x, plus 4 plus 4 is 8. These are in, sorry, let me put square feet, and this is in feet. Part C says, find the perimeter of the golf hole when the area is 216 square feet. Clearly, we have to see when 4x squared plus 12x equals 216. We're going to take that value of x, and we're going to substitute it in for the perimeter. If x is 2, it would be 10 times 2 plus 8, that kind of thing. So let's go ahead and subtract over 216. I see a GCF of 4 here, so I'm going to take that out. And I got x squared plus 3x minus 54. That factors into x plus 9 times x minus 6. The 4 will not be a part of my solution set here. X either equals -9 or +6. In this word problem context as per usual, -9 won't work out here, but 6 absolutely will. So when the area is 216 square feet, we do have an x value of 6. The perimeter was 10x plus 8. The perimeter was 10x plus 8, so 10 times 6 plus 8. 60 plus 8 is 68 feet of perimeter. And that is your golf hole. Sorry, this was number 9. That was number 9, my bad. And that is part C. That is our final step. And that is the end of this video and the conclusion to this chapter in cumulative assessment as a whole. So guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching, and I hope that you can find everything you were looking for. If not, go back, check the description section down below and see what you're trying to find, be it from playlist, timestamps, graph paper. I guess I need graph paper. A PDF of this information, all that jazz. So guys, I'll see you in chapter 3 when we start graphing. I might be doing some things different from the book. I don't know how they go about teaching it. We'll figure out when I'm doing it then. Just brace yourselves. I'm going to work toward efficiency, of course. Take care, as a Steeler seemed to score in the background. And Garoppolo seems hurt. I will see you in the next one. Take care.